BC Chemistry, Unit 4, Carbon-13 NMR. So this will be the last video talking about nuclear magnetic resonance spectroscopy. I will particularly look at an isotope of carbon, which is carbon-13, produce the spectra that helps us to identify the nature of different carbon environments and therefore deduce a structure of a hydrocarbon chain. So with NMR, so far, how much do we know? The difference in energy needed to change spin state in a sample are all compared to a reference, which is tetramethylacetylene. So that peak is always the 0 on the scale. Then the energy difference required to change the spin state is manifested on the spectra in terms of chemical shift, and it's measured in ppm. So why do different nucleus require different amounts of energy to change their spin state? That is because the actual magnetic field experienced by each atom depends on the electrons on the neighboring atoms that will have a shielding effect on the nucleus in question. Therefore, the hydrogen in Ch2 group will be experiencing a different magnetic field compared to the hydrogens in Ch3 group. As a result, the chemical shift will be different. And this is why we always need to identify the carbon environments or hydrogen environments first before we can actually compare it to the spectra produced. Now, C13 NMR. Carbon-13 is a naturally occurring isotope of carbon with a nuclear spin. The most abundant element of carbon, which is carbon-12, does not really have a spin because it has an even number of nuclei. Carbon-13 doesn't really have a splitting pattern. So what we actually look at becomes very simple, which is number of peaks equals to number of different carbon environments. And since it doesn't really have a splitting pattern, the chemical shift is actually quite easy for us to confirm our deduction for in carbon-13 NMR. They don't really change too much. So here's the sample. Now you have 2 peaks for ethanol, therefore 2 carbon environments. TMS is the reference. There's no splitting patterns concerned. So it works more like a low-res hydrogen proton NMR. Well, let's look at this question. 2 isomers of C3H6Br2 have 2 peaks in their CNMR. What are they? Well, this compound does have 3 carbons. If it only has 2 peaks, it means that it must be somehow symmetrical in nature, so that 2 carbons are actually in the same environment. So of all the different kind of isomers we can write, there are 2 that actually are symmetrical in nature. One is that you have 2 Br, 2 bromines on the side, or you have 2 bromines in the middle. So which one is, I think it's D. Okay. There's some notes that we need to know in the background for CNMR. One is that because carbon-13 is a relatively rare isotope, so of all the hydrocarbon or organic compounds, we should say, it's unlikely for them to be adjacent within the same molecule. So you might have a C13 on one for one carbon, and then another C13 on a carbon on another molecule, right? So therefore, for that reason, it's unlikely for one molecule to have 2 carbon-13. Therefore, carbon-13 NMR does not have a splitting pattern. That's the reason, because overall, if we have a sample of it, there are like 100,000 of carbon-13, then we can totally expect that there should be a carbon-13 in each kind of the carbon environment in that particular sample. But if you zoom in to like one single molecule, it's unlikely that there will be 2 carbon-13 in the same molecule, especially for the simple organic compounds that we normally talk about. Okay. Also, for a similar reason, the peak area does no longer correspond to the number of carbon atoms in each environment. Okay. So in summary, for CNMR, the only useful information is the number of different carbon environments, and we also use chemical shift to help us to confirm our educated guess.